I will present you work, which is a part of a project which is granted by French ANR. And the name of the project is Microtip, and the aim is to design a micro gripper to grasp and manipulate objects at micro scale. So as you can see, I'm more like in robotics and automation rather than in sensor. For this work, we have several academic partners which are involved. The first one is LPPI, who's in charge of the chemical process and everything for the design. The second one is IEMN in Lille. This partner is in charge of designing and processing the micro gripper at micro scale. And I'm in with Versailles, and we are more in control and automation. So I will first present you the fabrication process and the experimental setup which has been used to provide results for both sensor and actuator mode, because this polymer has a capability to be used as a sensor or an actuator, and the ultimate goal would be to use it as actuator and sensor at the same time. And we have first results about that, and it completes the paper which has been submitted to IEEE sensor. So the IPN is made of 2 electrodes, and between these 2 electrodes we are using a membrane which is made of 2 things. The first one is for conductivity of electrons, and the second one is to ensure mechanical robustness. If you need more details about the chemical process to design that stuff, you may find it in that reference I can give you if you don't have time to take a picture. One particularity for this polymer is it can be used first as an actuator. In that mode, what we made is to apply a potential difference between the 2 electrodes, and it bends the polymer. For the second mode, for sensor, when a mechanical deformation is applied, we are able to measure an output voltage, but it's not in the same range as for actuator, so it's difficult to process the signal to sense and actuate at the same time. So we need to develop several models to be able to predict the output. The experimental setup for the results which will be presented is that one. So we have a DC motor which can be actuated to create disturbances on the IPN, and you have the dimension of this IPN at the top right. And we have 2 different kinds of deformation, the so-called positive and negative, to make sure that the polymer can react on both ways. First result for sensor mode. It was necessary to amplify the output voltage because it's just a few of microvolts. So we have basically 3 levels of amplification. And the second one is a differential amplifier, is to make sure that we can subtract an offset voltage, which can be due to mechanical pre-constraints or electronic drift. What we did is to apply periodic disturbances on the polymer, and we were able to measure the output with a gain around 1,000. We can see that we can measure both positive and negative deformation, and that measurement is quite repeatable. So after that, we made a zoom to try to derive a model of this sensor. At first, we can distinguish 2 phases. The first one is when the polymer is bent by the probe, and the second step is when the contact is broken and that the polymer is going back to its initial state. So it leads to 2 different equations that match the experimental data. In this equation, AS is the initial voltage value, 2S is a response time, and BS takes into account an offset voltage. We have also make sure that the model is still valid for different initial voltage values. So it seems to be to match the experimental data, and the model is black dotted. It's not very clear on this figure, but it seems to match the experimental data. For actuator, what we did first is to apply a square waveform with a given frequency and with a magnitude of plus minus 2 volts. And the system was linked to a resistor, and that explains the difference that we can have right here. That's the voltage of the generator, UG. UP is a voltage at between the two electrodes of the polymer, and the difference is due to a resistor which is serially linked to the system. And we were able to identify such model with some kind of parameter for sensor. So the next step was to find an electrical model, and we have proposed that one, which is quite simple, 2 resistors and 1 capacity. And the aim was to identify and to find the value of these parameters. And the model was simulated with Simulink. So the step response, which has been computed with the transfer function, is like this. With U0 is the voltage given by the generator. Tau is the response time, and G0 is the static gain. And everything only depends on the parameter taken in the model. So as a result, that's what we obtain. There is an output of the electrical model, the analytic function that we have proposed, and experimental data. And again, the response seems to match experimental data. All parameters were determined with initial and final voltage, and with respect to the constant time. The last result that we have here is to use the polymer as an actuator and to apply periodic disturbances. And what we would like to do is to be able to detect the contact between the probe and the polymer while actuating. That's what we did with the DC motor. We have exactly the same result as previously, but from time to time, what we can see is periodic disturbances that we need to clearly identify when performing, for example, manipulating tasks. So this is very first results that we have obtained with processing a very basic processing filter. What we did is to compute the difference between the model that we have derived and the experimental data. So what we obtain is, of course, the remaining signal is due to the disturbances. And what we did is to amplify this signal with a derivative filter. So we are able to detect the contact while actuating, but one problem is that we still have some peaks which are due to the waveform transition. For future work and conclusion, we already start to make the same setup, but at micro scale. What we designed first, it's that shape that was made by Lille. The lab is IEMN, sorry, and you have the address here if you want to check for other results. And the setup is made with photolithography and layer by layer process with spin coating techniques. Here you can see what happens when you apply magnitude of 2 volts and minus 2 volts. The micro actuator is also able to be operated in a vacuum condition, which is quite interesting for us as far as we are interested in micro robotics application. So here, compared to the paper, I chose to present more recent results, but of course we need to still more investigate, for example, for sensitivity, accuracy, and other things like that to give precise performances of the IPN. And at the end, I would like to thank especially Tien and Nguyen, who was in charge of this work in our lab, and also several partners, Cergy, one university in Taiwan, and the IPN in France. So thank you very much for your attention.